So section 1.6 covers matrix operations. I know I had said originally in the syllabus that we were not going to cover this section, but in looking ahead in the text and planning the next few chapters, I realized we should cover this stuff, okay? And it's not a super long section. There's only 2 homework problems, so just make sure you have a basic understanding by the end of this chapter. So what is a matrix? A matrix is an arrangement of numbers into rows and columns. So the rows are horizontal, right? So this would be a row, and the columns are vertical. So for example, here I have the matrix A, and matrix A is a 2 by 3 matrix, and it has 2 rows and 3 columns, okay? 2 rows and 3 columns. We always say the number of rows before columns, and to remember this, I think of RC, like RC Cola, which is not my favorite cola, if we're going to be honest. So if I'm given a matrix M, we refer to the entries in matrix M by Mij. So what that is saying is I'm taking in this matrix, I is the row and J is the column. So in the matrix above, in matrix A, I have the A sub 1, 1, so the element in row 1 and column 1, where those 2 intersects is 1. If I have an element in row 1, column 2, that's 3. And in row 1, column 3, that's going to be 5. Now, in row 2, element 1, that's going to be 2. Row 2, column 2 is going to be 4. And row 2, column 3 is going to be 6. So this is how we label elements in our matrix. A square matrix is what we're primarily going to be working with. A square matrix is said to have the number of rows equal to the number of columns. Okay, so this is an n by n square matrix where the middle entries are called the diagonal. Okay, so when I have a square matrix, the middle entries are called the diagonal. So let's call this matrix B. So its diagonal is going to be the element B11 and B22. Well, B11 is 2 and B22 is -5. So that would be the diagonal entries of our matrix B. And as long as the number of rows equals the columns, it's a square matrix. So I could have a 3 by 3 matrix or a 4 by 4, but we are going to be working primarily with 2 by 2 square matrices. So let's talk about adding and subtracting matrices, okay? So when we add matrices, we add them by their interior location. And because of this, matrices must be the same size. So I'm going to go ahead and add these, and I will get out a 2 by 2 matrix because I'm taking a 2 by 2 and adding it to a 2 by 2, I will get out a 2 by 2 matrix. So adding by column entries, that means I'm going to add the entry in the first row, first column of our first matrix to the entry of our first row, first column of our second matrix. So I'm going to take 2 plus 1. I do the same for row 1, column 2, for row 2, column 1, -6 plus 7. Now I move to my next column, column 2. So row 1, column 2, that'd be 4 and 5. And then row 2, column 2, that'd be 1 and -2. That's just going to give me the matrix. 2 plus 1 is 3, -6 plus 7 is 1, 4 plus 5 is 9, and 1 plus a -2 is -1, okay? We would subtract matrices the same way, except instead of adding their entries, I would have just subtracted them. I can also multiply a matrix by a constant. So let's let k be a real number. When we multiply a matrix by a constant, we multiply each entry by k. So let's say I had k times A, B, C, D. This would give me the matrix KA, KC, KB, KD. I'm taking that constant times each element in our matrix. So here I have a matrix and I'm multiplying it by -3. I'm going to get back out a 2 by 2 matrix, right? We aren't changing the size of our matrix at all. So I have -3 times -2, row 1, column 1. -3 times -1, row 2, column 1. -3 times 8, right? That's going to go in my row 1, column 2. And -3 times 4, that goes in my row 2, column 2. So I have -3 times -2 is 6. -3 times -1 is 3. -3 times 8 is -24. And -3 times 4 is -12. So I can multiply a matrix by a constant pretty simply. I can add them pretty simply. What gets a little more complicated is multiplying matrices. Okay, so we're going to do a couple examples of this. But when I am multiplying an n by m matrix by an n by k matrix, I'm going to obtain an n by k matrix, i.e., for matrix multiplication, the number of columns in the first matrix must be equal to the number of rows in the second matrix, okay? The result is known as a matrix product, okay? And it has the same number of rows of the first entry and the same number of columns of the second entry. So we're going to be focusing on multiplying 2 by 2 matrices, okay? So if I have a 2 by 2 and a 2 by 2, because these match up, I can multiply these together, and my result will be a 2 by 2 matrix. So how do I multiply matrices? What I do is I take the first entry in the first row times the first entry in the second row, and I add that to the second entry in the first row times the second entry in the first column. So I'd get A times E plus B times G. Now I do the same thing again. Let me change colors. So then, in order to get the entry in the first row, second column, I take our first row times our second column. So I take A times F plus B times H. And that gives me the entry in my first row, second column. So we're multiplying the rows by the columns. So in order to get the entry in my first row, second column, in my second row, first column, I'm going to take my second row times the first column. So I take C times E and I add that to D times G. To find the entry in the second row, second column, I take the second row times the second column. This is something that it takes a little practice to memorize, okay? So we're taking row 1 times column 1 to get the entry in row 1, column 1. We take row 2 times column 2 to get the entry in row 2, column 2, right? That's how we find our 4 entries. So let's do an example very slowly. So in order to multiply this matrix, what I want to do is take row by column. So I'm going to take the elements in row 1 and multiply them by column 1 to get my entry in row 1, column 1. So I'm going to take -2 times 1 and add that to 4 times 7. Now in order to get the entry in row to column 1. So right here, I have to take row 2 times column 1. So I'm going to have negative 6 times 1 plus 1 times 7. Now to get my entries in column 2, for the first row entry, I have to take row 1 times column 2. So I have negative 2 times 5 plus 4 times negative 2. To get the entry in my second row, second column, I'm going to take row 2 times column 2. So I have negative 6 times 5 and 1 times negative 2. And the more you do this, the more you will realize the pattern it is following. So this would give me negative 2 times 1 is negative 2 plus 4 times 7, that's 28. Negative 6 times 1 is negative 6 plus 1 times 7 is 7. Negative 2 times 5 is negative 10 plus 4 times negative 2, that's negative 8. Negative 6 times 5 is negative 30 plus 1 times negative 2 is negative 2. So I'd get 26, 1, negative 18, negative 32 is the product of these two matrices. So there are two special types of matrices we're going to come across, and those are zero matrices and identity matrices. Okay? If I have a zero matrix and I take that zero matrix, this is the zero matrix, times any other matrix, the product's always going to be 0. Let me show you why. So let's practice our matrix multiplication. 2 times 0 gives me 0 plus negative 6 times, plus, oof, okay, too much coffee. So I'm taking row times column. So I'm going to take 2 times 0, that gives me 0. I take 4 times 0, that gives me 0. Next I take negative 6 times 0, which gives me 0. Negative 1 times 0, which gives me 0. I then take 2 times 0, which gives me 0. And 4 times 0, which gives me 0. Last, I take negative 6 times 0, which gives me 0, and 1 times 0, which gives me 0. So I get a 0 matrix. And this makes sense, right? If we had 7 times 0, we'd get 0. So a 0 matrix turns everything to 0. Next, we have an identity matrix, okay? An identity matrix is sometimes written I sub n, or just I, and it's the matrix with all ones on the diagonal and zeros as all other entries, okay? The product of any matrix and an identity matrix results in your original matrix. So if we think about multiplication, typically 1 is the identity element, right? Because 1 times any number is just going to give you that number back, right? We call it the identity element. The same thing is true for the identity matrix. So let's go through and do some multiplication. Two times 1 plus 4 times 0. Negative 6 times 1 plus 1 times 0. 2 times 0 plus 4 times 1, negative 6 times 0, plus 1 times 1. 2 times 1 is 2, plus 4 times 0, that's 0, so I just get 2. Negative 6 times 1 plus 1 times 0, that's going to be negative 6 plus 0, so negative 6. 2 times 0 is 0, plus 4 times 1 is 4. Negative 6 times 0 is 0, plus 1 times 1 is 1. See how our new matrix looks exactly like our original matrix. Very exciting, I know. The next thing we need to talk about is matrix transpose. So when I'm transposing a matrix, which we write AT, is the matrix obtained by writing the rows of AT as the columns of AT. Okay, so here's AT. I want to take the row and write it as a column. So row 1 then becomes column 1, and row 2 becomes column 2. If I had A was A, B, C, D, A transpose would be A, B, C, D. A, C, B, D. I took my row and rewrote it as my column. I then took my second row and rewrote that as my second column. We can also do this for a 3x3 matrix. So let's go ahead and try this out. I'm going to take my first row and rewrite that as my first column. I'm going to take my second row and rewrite that as my second column. And I'm going to take my third row and rewrite that as my third column. So that's how you take a matrix transpose. The last thing I want to talk about is an inverse matrix. Okay, so if I have two matrices, right, and if I multiply them together, B times A and A times B, then B is the inverse matrix of A, and we write A to the negative 1. And that's what we call that. B would be A to the negative 1. If A has an inverse, we say it's invertible. First thing I want to point out, it's important to note that typically AB does not equal BA when multiplying matrices. Unlike regular multiplication, it's not commutative. Okay? If I take two matrices, right, and I multiply them together and I get back the identity matrix, that's kind of similar to the concept of multiplicative identity. Remember, the multiplicative identity of two numbers would get you back to 1. So if I had 2 times 1/2, that gives me 1, not 2, okay? These two numbers are multiplicative inverses. Multiplicative inverses. Okay, so in order to tell if something has a inverse, right, we need to take the determinant, okay? And the determinant requires I multiply my diagonal times what remains, the diagonal the other way. Now this is the determinant just for a 2x2 matrix because that's what we're working with in this text. So my determinant is going to be AD minus BC. And a matrix only has an inverse if its determinant doesn't equal 0. It can be negative, it can be positive, but we can't have a determinant equal to 0. So let's determine if A has an inverse. I'm going to take 2 times 1 minus 4 times negative 6. That gives me 2 plus 4 times negative 6 is negative 24. Make that a positive 24. So I have a determinant of 26. So yes, A has an inverse. So here's the homework. It's only 2 questions. They do have multiple parts though, so sneaky, sneaky. I wanted you to know that I did post some matrix worksheets on our Lantern. I do not expect you to do those. Those are not homework. They are just guides. They've been posted and they already have the solutions. So if you have any questions, feel free to shoot me an email and I can make some more videos and answer any questions you may have.